Okay, so section 12.7 is triple integrals. And where you would need like a triple integral, for instance, if you wanted to find the center of mass for a three-dimensional object, okay, where its center point is, you would need triple integrals for that. The double integrals would get you the center of mass for a lamina, but for a three-dimensional object like a rock or something like that, you would need triple integrals. In the figure here, they have a well, not a region, but a solid in the XYZ plane. And what you can do is you can take little pieces of volume. You see that? Little pieces of volume. That little box there has volume delta y times delta x times delta z. Okay, and based on this, you can form a triple sum. A triple sum. Okay, and here you take the function at each point in that solid and you multiply it by a piece of volume, and then you add up all those values, and that is going to become a triple integral. So really, a triple integral is just the next natural extension for a double integral. And you might wonder, is it possible to have more than 3 integrals? Can you have like 4 integrals, 5 integrals, more integrals? Yes, you can. Like in statistics, there's a concept called order statistics where you can have a lot more integrals. So basically, think about how you computed double integrals. Well, with triple integrals, it's just a natural extension. Okay, so well, Christopher, you're right. You can use triple integrals to find volumes as well. You can. In fact, I'll mention this, your MATLAB assignments, and I'm going to, of course, talk about the ones you turned in at the end of class, but the new MATLAB assignments, MATLAB assignments 5, 6, and 7, are posted in Blackboard under MATLAB assignments. And they're going to be due on Friday, April 23rd, 3 weeks basically from today. Now, I know that weekend you have an exam to worry about, but the due date is before the weekend. Okay, and I assume you're not going to wait till the very last minute to work on those. But at any rate, I'm just mentioning, if you, because one of you had asked me about getting the MATLAB assignments ready, and they're ready, and they're going to be due on Friday, April 23rd at midnight. And there, if you look under announcements in Blackboard, there's information about a late day and all that. Yeah, I completely agree with what Christopher's saying here. He's saying that the snow ice cream problem that we talked about actually used triple integration, and it is simpler in the sense that in a sense it is simpler, and you're using triple integrals. But sure, I completely see what you're saying. And then Eric says in string theory, you're dealing with 10 dimensions. Okay, well, I'm not a string theory expert, but all right. So how are we going to handle these triple integrals? Of course, the obvious concern is finding the limits. Okay, so I'm going to go here to figure 2. Okay, figure 2 in the book has a type 1 solid region, and the region the region you have a like, how do you, I want to say this the right way, you have a solid in space. How do you bound the solid? Well, you can bound the solid by having a surface above and a surface below. Okay, and that's what those U2 and U1 functions are. The U2 function is bounding surface above, and U1 function of x and y is the bounding surface below. So if you wanted to have a triple integral where your region E were described as you see in figure 2, okay, and that's they have it like they have it written out this way: set of all points such that Z is between the bottom and the top surface, and X and Y coordinates are in region D in the XY plane. If you wanted to find that triple integral, this is how you would do it. So dz now instead of dx, dy, dx, you have dz, dy, dx. Okay, because dv is a volume, and to get a volume, you need to multiply a base differential. A length differential times a width differential times a height differential. Hence, dz, dy, dx. So you see, you can iterate the iteration that you're used to doing with double integrals. You can do with triple integrals. All right, and the book really has some very nice graphs, and I think we should make use of the book here. All right, so okay, now the thing is, what about the other limits? Well, the surface is bounded above and below by z equals, below by z equals u1 of xy and z equals u2 of xy. But then it's over this region D. Well, the region D, now we're talking back to double integrals. You have a function, a y function below, y equals g1 of x, a function above, y equals 2g of x, and then you have x limits of a and b. They have a figure here. Let me get it here so you can see this. See that? Hold on. Let me get it down a little bit. Hold on. Yeah, but let me get it down a little bit more here. So, hold on. I don't know why that. Get that off there. Okay, so yeah, this is in figure 3 a type 1 solid region. You see how you have the boundary surfaces above and below, and then the region D has your top and bottom functions, g1 of x and g2 of x, and then limits go from a to b. Okay, that's how you get those the limits, and then based on that picture, hopefully this makes sense. Are there any questions so far? All right. It's kind of natural, right? Well, now we can also have a situation, that was a type 1 region, but if we have a type 2, they call it projection here, but I don't want to get involved. I don't want to get into the terminology too much here. But here you have a surface that above and below, bounding above and below, and then in the xy plane, you have left and right functions, h1 of y and h2 of y, and then limits go from c to d. I mean, you could have this situation. Okay, you could have that situation. And if you have that situation, then these would be this would be your integral. So dz would be the same limits, but instead of dy dx, you have dx dy. Okay. Are there any questions so far? Okay, well then let's continue on. Let's continue on here. So example 2, okay, example 2 talks about triple integral over a tetrahedron. Okay, so in this problem, you're computing a triple integral, and what's your region E? Or I'm sorry, what's your solid E? What's your solid E? Well, it's a tetrahedron bounded by 4 planes. Okay, and so we have to get the limits. We have to get the limits. So it's always best to draw a picture if you can. And they do have a picture here. Okay, they have the plane z equals 0. That's the xy plane. So that's your bottom surface. And then the plane z equals 1 minus x minus y. That's the surface above for your solid. And then the tetrahedron is bounded by the planes x equals 0, y equals 0. That would be the yz plane and the xz plane. Okay, so it's bounded on the side and the back, and that's your region D, or region E. I should say your solid E, solid. It's a solid. All right, and so note that solid, and if we were to project that solid down into the xy plane so that we could identify what our region D is of integration, that would be what you see in figure 6. Okay, please stop me if you're uncomfortable. These type 1 regions, incidentally, that they talk about, they call them, well, they call the region E a solid region. Okay, I like to think of it as a solid, but they call it a solid region. And a type 1 solid region is where your boundary surfaces are above and below. So okay, here then is the triple integral. Here's the triple integral. So the tetrahedron is bounded below by the xy plane, that z equals 0, and then it's bounded above by the plane y minus x minus y, z equals y minus x minus y. And then if you project that solid region down into the xy plane, you'll get a triangle that's bounded below by y equals 0, that line, and above by the line y equals 1 minus x. And then the limits go from 0 to 1. Okay. So when you have situations, actually, when you have situations where you could have where you have a, I want to say this the right way, like the ice cream cone problem. The ice cream cone problem, you had a sphere bounding above and a cone bounding below. So in order to use double integrals to find the volume, we had to subtract one double integral from another double integral. But if we use triple integrals, we could find that volume all in one, just with one triple integral. Okay, and maybe maybe in our next class I'll do one do one like that with you. But for now, let's just Okay. So far, are we comfortable? So far, are there any questions? Okay. Well, let's keep, Ryan's good. All right, let's keep going. Let's keep going here. Okay. So now, oh my goodness, we have a type 2 solid region. So we learned about a type 1 solid region. That's where the surfaces are bounding above and below. A type 2 solid region, hold on here. I want to get it to show. Okay, what are they talking about here with this type 2 solid region? Okay, well let me show you a picture here. Let me show you a picture of a type 2 solid region in figure 2, or I guess figure 7, sorry. You see this? You have surfaces that are functions of y and z that bound the surface to the left and the right. Okay, and so region, like the solid region E, it would be it's more convenient to use, well, let me ask you, for the triple integral for this type 2 region, what do we integrate with respect to first? dx, dy, or dz? Well, what your bounding surfaces are, well, if we were, Eric, if we had a type 1 solid region where the bounding surfaces were above and below, we would do that. But in this case, that's right, Diadath, we would integrate with respect to x first, because our surfaces are x equals a function of y and z. And so for this situation here, this would be, hold on, yeah, this would be your triple integral. So what they're doing is they're saying, well, integrate with respect to x first, and then you can decide whether you want to do dy dz or dz dy for dA. So like when you had like in like section 12.3, when you had dA, you could do dx dy or dy dx. You could do dy dx or dx dy depending on whether you had a type 1 or type 2 region, right? But now, since we have dz dy dx, how many orders are there in which we could do the integration with dz dy dx? How many different orders are there? More than 3. Well, not that much, Ryan. Tell you what, let me go to the whiteboard. Hold on. All right, hold on. Let me go to the whiteboard here. So we have dv. Maybe I'll use my little thing here. One moment. Where's my pen? Here it is. Okay, we have dv. dv. That's right, Eric. Good. You're used to, I don't know why it's doing that. You're used to Hold on. For some reason, my pen's not writing. Hold on. All right, I'll go to the mouse. dz, dy, dx, right? But you could do dx, dz, dy. You could do dy, dx, dz. I mean, there are 6 orders total. Those are 3 of them. Right? And sometimes, it's important to, you'll have a problem later on that from 12.7 that's going to make you look at the 6 orders, okay, because it helps you understand triple integrals. But there are 6. There are 6. 3 times 2 times 1. For the first choice, you have 3 choices: dz, dy, dx. For the second choice, you have 2 choices left, and then you have just 1 choice for the third. So that makes 6. All right, let me get back to the book here. Hold on here. Okay, so there's a type 2 region. Now, here's a type 3 region in figure 8. They have a type 3 region where the surfaces bounded on the left and the right are functions of x and z. That's what a type 3 solid region would look like. And so in that case, okay, hold on. Yeah. Maybe I can get this a little lower. In that case, type 3 region in figure 8, that's what your triple integral would look like. Okay, so are there any questions on that? All right, let me keep going here. I want to go a little bit longer here in chapter 12. So really, which order of integration you use depends on the example you're talking about. Okay, so in example 3 here, they want you to evaluate this triple integral where E is the region. Hold on, let me see if I can get it all to show. Example 3. E is the region bounded by the paraboloid y equals x squared plus z squared. Oh, wow, you're used to always seeing z equals x squared plus y squared. But now you're seeing y equals x squared plus z squared. So is that parabola going to open out along the y-axis, the z-axis, or the x-axis? Good, the y-axis. That's right, Christopher. That's right, Robin. And so, and here's the. Let me get the picture here. Here's the picture. So would this best be, let's see here, I want to say this the right way. Would this best be treated as a type 1 solid region? I'm sorry, is the solid region E a type 1 region, a type 2 region, or a type 3 region? Hold on, there was a comment there. That's right, Ryan. It's a type 3 region. It's a type 3 region. And so that means that we should integrate with respect to y first. Okay, so the surfaces here, what are the two surfaces in figure 9 that are bounding the solid? The paraboloid and the plane. That's right, Ryan. So see, the paraboloid, I mean, the paraboloid is the surface that's bounding on the left. Y equals x squared plus z squared is bounding on the left. And the plane y equals 4 is bounding on the right. So if we were to use, I want to say it's the right way, if we were to use treat the region, the solid region E as a type 2 region, the triple integral hold on here, would look like this. Okay, take a moment and think about it. And then if you do the inner integral, you're going to get what's on the right here. Because you're taking 4, well, the antiderivative of the square root of x squared plus z squared with respect to y is just y times the square root of x squared plus z squared. So you just substitute in 4 and x squared plus z squared, and you'll get what's there highlighted on the right. So far, so good? Are there any questions? All right, well now we got to decide about our region D. And they denote it as D sub 3 because the solid E is being treated as a type 3 solid region. So it's a region D for a type 3 solid region E. So we got to project, okay, that solid region E into what plane? What plane would we, to determine the region D of integration for the last two integrals, if we project that solid region E into a plane, what plane would it be? Let me ask you this. Would the projection of that paraboloid, what shape would it form? What shape would the projection of that paraboloid along the y-axis, if we projected it into a plane, what shape would it form? Well, it has to be a two-dimensional region. It's going to be a circle. It's going to be a circle. If you project that paraboloid into a plane, it's going to be a circle. Now, what plane are you projecting it into? The XZ plane, the XY plane, or the YZ plane? What plane are you projecting that region into? It will go into the XZ plane. Diodoth, if the paraboloid were an up and down paraboloid, then we would project that paraboloid into the XY plane. But because this paraboloid is opening outward along the y-axis, if you compress that paraboloid, you're going to push it into the XZ plane. And so you'll get a circle in the XZ plane. Okay, excellent, excellent. So you see, I'm trying to focus here on the geometry of triple integrals as opposed to computation, because I think computation you can do. Certainly will have opportunities to practice that, but the geometry is critical because, you know, we have to have the geometry down. Okay, so, oh man, all right, so region D3 is a circle. Oh, when I hear circles, what type of coordinates do I want to use? Do I want to use, you know, polar? That's right, good, that's right, Christopher. So in the book here, if we go to, you know, here's figure 11, where they project that solid onto the YZ plane, we're going to use polar coordinates. But in this case, x squared plus z squared would equal r squared. And x would equal r cosine theta, and z would equal r sine theta. You know, you have to change the definition, because you're used to, oh, x equals r cosine theta and y equals r sine theta. But you're not in the xy plane, you're in the xz plane. So x is going to be r cosine theta, and z is going to be r sine theta. Okay, you just have to kind of think simply about it. Okay, and so when we do that, then, okay, well, we replace x squared plus z squared by r squared. The r limits are going to go from 0 to 2, and the theta limits are going to go from 0 to 2 pi. And it turns out we're going to get 128 pi over, 128 pi over 15 for that triple integral. Okay, are there any questions on that? Okay, well, let's go a little further. Let's go a little further here. All right, in section 12.7, we should look at applications of triple integrals. Okay, applications of triple integrals. Here's an application that one of you was referring to, actually, finding the volume. So if you want to find the volume of a solid E, just take the triple integral over that solid E, and the integrand is going to be 1 dV. Yeah. Now, why is that? Why is that true? Well, think about what they're doing here is below. If you have a type 1 solid region E, then you're going to integrate with respect to Z first. You're going to integrate with respect to Z first. Hold on, let me make that. Yeah, you're going to integrate with respect to Z first. And Z is just, well, when you, what's the antiderivative there of 1 dz? What's the antiderivative of 1 with respect to dz, the number 1? Z, right, good, Christopher. And so when you plug in U2 and U1, you'll get the difference of the top and bottom surfaces. Okay, and notice that when we used, and now it's a double integral, right? So a double integral where the difference, where the integrand is the difference of the top and bottom surface. And recall the ice cream cone. We had a difference of double integrals, and this should help you connect the idea that we can use a triple integral to get a volume, because essentially, well, we already, for the ice cream cone problem, we took the difference of 2 double integrals, okay, one for the surface below the sphere, and one for the volume, the volume below the sphere, and one for the volume below the cone. And the difference was then, of course, over a region D, over a circular region, but the difference was then the volume of the ice cream cone. So who's liking this now? Who's liking the triple integrals for finding volumes? All right, John likes it, Christopher likes it, Robin likes it, Ryan, excellent. Now, of course, for your, your third exam, you can't use triple integrals because the third exam doesn't cover section 12.7. Okay, you have to work with double integrals. And there's nothing wrong with that. But yeah, it's absolutely cool, absolutely cool. Okay, let me do a little bit more here. Okay, so mass. Okay, center of mass. So mass equals density. Density is mass over density is mass divided by volume, right? Hold on here. Yeah, density is mass divided by volume. So mass is density times volume. And so here's the formula for mass, but now we're talking a mass in 3-dimensional. We're talking a solid region in 3-dimensional space. And if you want to find then, hold on here. Okay, if you want to find the moments about the coordinate planes, so you're not going to find moments about x and y axes because you're in 3-dimensional space. So you have moments about the 3 coordinate planes. That's how they're defined. Okay, and so the center of mass, this is analogous to what you learned in 2 dimensions, except you're talking about distance now from a plane instead of distance from a line. You're talking from an axis. You're talking about a distance from a coordinate plane. So the moment about the YZ plane, you have an X there in that formula. The moment about the XZ plane, you have a Y there. And the moment about an XY plane, you have a Z inserted in the integral. So how many maybe have seen this in their physics class? Have you encountered this yet in your physics class, these center of mass over a solid, I'm thinking maybe, well, you have to have triple integrals, right? But all right, well, let's keep going here. Let's keep going. So no problem. So then here is your formulas for the centroid. There's your formula for the centroid. Oh, hold on. Chris says most 1 to 200 level physics classes don't use triple integrals. Okay. Okay. All right. Well, you'll be ready when they do, right? So let's look at an example dealing with center of mass. Well, no, I'm going to stop there. The example 5 deals with an example center of mass, but I think this is a good place to stop. Um, are there any questions? Okay, let me stop the recording.